Okay. Okay, before I start where I left this. Okay, there was just one question by somebody about this, just a few clarifications that I start with, and then I will do a recap of what we discussed last time and then finish up before moving on to introducing predicate abstraction. So is it clear as to how you, from given a CFG of a program on the right side here, that the fixed point equations that need to be solved are derived? Okay? Because I want you to simulate this this algorithm that I've described here, not only on this example, but also on a few other examples, and make sure that you understand it. Okay, so it is first you have to get the equations starting from this, from the program, in the CFG representation program, and then you start propagating the values. And the idea is to solve this simultaneous fixed point equations, because they can have circular dependency of these values in this. So I want to first make sure that you understand how you get these equations. Sandeep, you know how you get these equations? So there's one equation for representing the value at each of the locations, and the value means that in the abstract domain, which is supposed to represent an inductive invariant or an over approximation of it. Either of you? Either say yes or no.
Yes.
Well, then say what? Then ask the question. No. Yeah, answer is what is expected if you know. How do you get
Hello?
Yes, I can hear you.
Yeah. So you just follow the control flow graph, and basically for every outgoing edge, you put a whatever statement that edge has, you evaluate the you use the abstract semantics, and it will be the join of all of the edges that are incoming into a location.
Correct. So it is the post. Okay, so the post in the abstract domain is what you compute. But there's one important distinction that you will have to be aware. So for example, yeah. So the value at x2 is is the result of propagating the value from x1 by applying the post, which is what this double square thing really represent. But the hash symbol is on the abstract domain. But when you put this equation, there is an assumption that yes, whatever value that you have, with yes, the propagated there, except that there could be nodes which have multiple incoming arrows. Okay, like which represent the heads of loops. Okay, like in location 1, x1. So there you have to do a join of the two things. The equation, the expression on the right side, is the result of doing a join on the result of propagating from each of the edges. Okay, that is important. Yeah, you recognize that. No? So when you have the CFG with multiple loops, etc., that will be automatically be taken care of. That's what I want you to understand. Then, like for doing clean iteration, you start initializing the value at each location to the bottom, and then you do the propagation until you until all of them saturate, all the values at all the locations saturate using this algorithm. Okay, by once you propagate, you remove that, and then you add all the target locations, and you keep doing it until they propagate. Okay, good. Yeah, I hope you understand that. Okay. Okay. So now, so like last time, what we're saying is this algorithm need not necessarily terminate, especially, I mean, for finite systems, finite state systems, it should terminate because we have removed through this ordering, not ignoring any particular location, gratuitous reasons for reasoning. But for infinite state systems, you couldn't, it need not terminate. And even for finite state systems, clean iteration could end up degenerating into having to unwind or iterate through the loops too many times that won't scale in practice, and therefore we do a variation of the clean iteration. You could say an acceleration on a clean iteration, for a better word, using by applying using a widening operator at each point. Okay, and that's what I'm doing. Is this big enough? Maybe I can make it a little bit bigger here. Okay, and that's what is I'm illustrating here. If this works, yes, it works. Okay, so normally the left side is clean iteration. That okay, who else is here? Let's see. Good, I have Diganta. Yeah, and so you, instead of applying F in the normal cleaning iteration, what you do is you start with bottom, and then at each step you compute the next element in this widening chain by applying the widening operator to the previous element, and the result of applying F, the higher order function, the collecting, the function that defines collective function on that. Now, the widening operator, as I said, satisfies two properties. Is an operator, is a binary operator, such that it returns something which is an upper bound, which is greater than either of its operands. Okay, and it is also such that on any, when applied to this way, on any iteratively on successive elements of any ascending chain, it eventually stabilizes, because at each point it gives something which is greater than each of the argument, but it does not keep increasing it. At some point, it is defined in such a way that it stabilizes. In the sense, the result of applying it will be less than the previous application. Note that this is itself an ascending chain, because F is a monotone operator. So this one is, after one in application, it is greater than either of these two operators. And since it's, F is something that gives at least something that is as big as its argument. So this is indeed an ascending chain on which you're applying the widening operator. Okay, and that's what you do. Okay, so intuitively, what you're doing is you're looking at the previous, widened and accumulated value, and then the next value when you apply it to when you apply f on it, and see kind of the trend, and then you kind of extrapolate to make it even bigger, and that's what is happening. And since the second condition here, when you apply it on an ascending chain, the fact that f is monotone guarantees that as long as it's increasing, this is an ascending chain, and therefore eventually it has to stabilize in the sense that the result of applying the thing should be less than or equal to the previous value. Okay, and since this is itself an ascending chain, and the way you are applying it to is the result of applying f to the previous argument, and that's what is used as the second argument to the widening operator. So eventually there must be a point at which the widened value will fold itself into itself. Okay, and that's what is happening. And since the second argument is always the f of that, there is so at that point, you see, I mean, that's so one way to check if you've reached that is doing this a check, okay, to see if the result of applying f on your previous widened accumulated widened version of the accumulated value is it is really increasing. Okay, as long as it's increasing, it is still this the widening chain is still increasing. The moment that, since f is monotonic, the so one way to check is when it becomes if the second argument, the result of applying f itself, is within the previous value, okay, which is what the first argument to it is. At that point, of course, you would have this chain would have stabilized, right? Because if then f is no longer increasing. So this is a point at which it has become reductive. So you would have skipped. Okay, you would have reached this point. Okay, in the sense, this result of applying widening is it kind of forces you to overshoot your fixed point region and go into the region in which the element becomes reductive. That is, further application of f can only reduce them, and that's what is at that point. Certainly, you have overshot the fixed point and got into the reductive region. So that is you might as well stop at that point. Okay, and that's what this check does. Okay, of course you could independently just check, and since that if at each point, if the new thing that you get is less than or equal, this is another way to check that that you have reached the reductive, I mean the post fixed point. That's what it's called. Okay, so this check checks if the latest value is a post fixed point. A post fixed point is one in which further application of f will not enlarge it, but rather it reduces it. See, at that point you have reached the post region, and that's why at that point this would be whatever that you have would be something which is greater than that includes the least fixed point. Okay, and you can actually that's because that you have reached that region, so you know that, but you can also prove that that it is greater than or equal to f star, because by comparing it by induction, by comparing these two chains. So because at each point, what you get here on the right side, the result of applying the widening operator, is greater than this one, okay? As long as it is increasing. And the moment it becomes a post-fixed point, it is no longer increasing. Therefore, it has to contain f star, because otherwise, because this clean chain starting from a bottom is something that is, the first time it doesn't, keep on strictly increasing is when you hit the fixed point, okay? But since at each point, as long as this thing is increasing, the widened value is greater than the corresponding step in here, when it, no longer, when it stabilizes, no longer increases, then it has to be, greater than or equal to, f star. Okay, and that's what it means. This check really ensures that it is in the in that region that in the region of the post-fixed points. Okay. And so that's what it guarantees. So what widening, following the widening chain is not only, because the widening operator has to be defined in such a way that it widens these values, accelerates convergence. And the guarantee of convergence is by the definition of the widening operator itself. It extrapolates such that eventually the application of f itself. So two important points is there is a particular kind of ascending chain on which this widening operator is applied, which is where the second argument is obtained by applying f to the previous widening value. That's why it ensures that you overshoot the f star and get into something which is a post-fixed point. A post-fixed point is one which contains all the fixed points, but itself need not be a fixed point. Okay, that's why, as you can see, when you get to f delta n minus 1, okay, f delta n, when you apply f delta n, it can be going down the chain, unlike f star, which is which could be less than that. Which here it is, it doesn't, it stabilizes. I mean, it's a fixed point. Okay, whereas here, a post-fixed point, when you apply f, need not be a fixed point, and but it is it's guaranteed to be an over approximation of the fixed point. Okay, and that's what happened here in this this example. Okay, so I hope I don't want to repeat this example. If you have any questions on this, on the way that okay, in this operator itself, you understand. Huh? Where is the operator? Okay, so I'm applying this widening operator. So I hope you, it looks at the second argument is the new f applied to the previous value that you got. And that's why it looks at the lower bound. And if the trend is that the lower bound is being extended, then it extrapolates. This is one way, okay, to ensure that on the negative side. Otherwise, similarly, if the trend is that u2 is increasing, then it extends it all the way to infinity. Okay. So one thing that I want to show in this example, okay, is this one. As you can see here, So since it overshoots -1 infinity, that the widening chain stabilizes to here, is really not it is indeed a fixed point for this program, okay, for this loop, okay, because indeed, because here it keeps on increasing. Here it is not a fixed point because, can anyone say why? For this program, which is a terminating program, okay, because here all chains here are produced by iterative post computation of the body of the loop, okay, right? So all the chains of this program are bounded, right, by 1000, okay? I mean by 1000, and that's what this widening is ignoring. So it has overshot in all the chains here. They end at 1000, the chain here, and since you've overshot it, therefore, if you don't do anything else and you use that, so that's an over approximation of the actual fixed point that you can get here, okay, which so it should be between 0 and 1000, and that's why when you use that and then propagate it on the exit edge, you end up getting let's see, so you end up getting 1000 to infinity. Now, your widening operator could have done some analysis, if it had a magic box, if it knew that all the chains were were bounded in this case, then maybe the widening operator, instead of extrapolating the upper bound to infinity, it could have curtailed it to 1000. Okay, that if indeed you could predict what the future is of the which you can do only by iterating. But if you had some heuristics, etc., that guarantees that the bound, then you could have done that. So short of that, here the idea of widening is I'm okay to overshoot it, because as long as I generate some an over approximation of fixed point, maybe it'll work sometimes to prove the property that I'm interested, or it may be even a fixed point in some cases. But you can it can be too weak, too coarse of approximation of the actual fixed point for the purpose at hand, which is what has happened in this example. Okay, so the question is, how do you regain that? Okay, so that precision, and that is what you do by, since it's an over approximation, it's a post fixed point. As I said, a post fixed point is one in which includes all the fixed points, but it is on a descending chain. Okay, by definition, it's on a descending chain. Therefore, what you can do now is you can regain some of the precision that you get by applying clean iteration, simulating a descending clean iteration. Because at this point, any application of f, since it's reductive, it'll keep on reducing it. Okay, and therefore, eventually, you would end up with either, if you follow the entire chain, you will end up with a fixed point. Okay, that descending chain will get here, or that is one way to improve the precision. But of course, there's no guarantee that this descending chain ending up at the fixed point may terminate. So one way to regain, but you can always use a truncated descending chain. You can do this descending cleaning iteration. One way I'm suggesting, one way to regain is do as long as you care to, and but it is still sound to do that, because what you get here is certainly something which is every step, every thing here that you get is an over approximation of an eventual fixed point. So one method, one way to regain some of the precision is you do a descending cleaning iteration, a truncated descending cleaning iteration. If doing a complete cleaning iteration to a fixed point is not practical, okay, and that's what mostly the tools actually use. Okay, one of the strategies that it uses. So what you can do is here is the overall method. So you do the classical analysis. It's usually the analysis that are implemented in most abstract interpretation tools. And so 3 phases. One is you can do standard cleaning iteration up to a certain point, okay? And then if that is up to a certain bound, which is pragmatically decided, after that you start using the widening operator, okay? With some given widening. Several choices that you can have. I've shown you one, and that's what is called delayed widening. Delayed widening is one if you decide to first start with a cleaning iteration, standard cleaning iteration, and then switch over to the widening until you reach convergence on the widening sequence. In which case you will have that is when you reach a post-fixed point. Okay, and then you do a truncated descending sequence. If going all the way to fixed point is not feasible. Okay, and that's what you do. And I'm going to illustrate that on an example, on this previous example, which gave something which was too coarse and over approximation. Okay. And how that works, let us see. Okay, so you saw that what we did through the widening sequence gave us -1 to it stabilized at -1 to 1 to infinity, which is an over approximation of the actual fixed point here. Okay, because here the value of x can get only the upper bound is 1000. So now you start, doing descending cleaning iteration to regain precision. So what are the nuts and bolts that you need to do the cleaning iteration? What is the F here? Okay, that's what. So without doing descending cleaning iteration, just propagating it across the exit condition gave you just 1000 infinity, which is not good enough to prove this property because it is too coarse. Therefore, instead, what you do is now, in order to do a clean iteration, what is the F that you will have to? What is the F for the this example? As you know, F is the post here is the result of executing the body of the loop under the condition x is less than 1000, because you execute the body only under the condition x is 1000. Therefore, so what you do is, and your F is, that's what your F is for doing the clean iteration that you would use, which is the post is over x is equal to x plus 1 after checking the condition x less than 1000. So that's what the post of X, first checks X is 1000 and then increments it. And that's what it does. Applies that the post of these two pieces of the program, and then takes conjunctions. And that's what is the result of propagating this fixed point across the exit. No. Sorry. Yeah. Correct. Okay. So then what you get is the result of applying that will be, So here you will get -1 to 1000. Okay. Because it truncates it, because the way that you, once you propagate this descending chain, once more you will get, so it truncates it to between -1 and 1000. And then when you, something is, So, and then you get, that's what you do. And, so you end up, this will become -1 to 1000. And when that is propagated, you get, this will improve to 1000 to 1000, and which is not, so this is feasible, and therefore you don't get the spurious error. Okay, and that's how that you regain the lost precision. Okay, any questions here? Okay, so here is another example. I will leave that as an exercise, for you to do, to make sure that you, what you'll have to do is you have to compute the post of this body here. And you need to do this, both widening and the post descending, truncated descending thing only at the head of the loop, especially the widening. You only need to do at the head of the loop and not after at every location. And that's what I call as the cut point here. Now, Kleene, yes, descending Kleene, truncated descending Kleene is one way to do. So there's a question of why can't you actually define a dual of the widening operator, which would not, which would lead to maybe faster convergence on the descending chain. Okay, that indeed is possible. Just like you did an through the widening operator, you did an accelerated, convergence. On the descending chain also, you can define a dual of this operator, of the widening operator called narrowing operator. And this one is, it's defined in such a way that it gives something which is, which is less than or equal to x1. Both the arguments to which it is applied, but it does not. Okay, it is something that narrows it only as much, not too much. Okay, in the sense that it is bigger than anything that is less than both these arguments, and then you can apply and then something to the widening condition. If you had this condition that you impose this condition that it has to be such on all descending chains, it has to do the reverse of extrapolation, which kind of narrows it such that it eventually stabilizes on descending chain, even when it is infinite, can work as well. But in practice, mostly people, most of the tools use truncated descending chain as it is good enough to get the required precision. Okay? But you can also define narrowing operators. Now, I can't get into the details of some of the narrowing operators that work in practice. Maybe if we have time, I will get in some later lectures. Okay, so in summary, okay, this is something. So where does imprecision come from when in static analysis tools? So one is in the way that you define abstract transformers. Okay, so there you can defining the most precise abstract transformer. Could be those abstract transformers could be not as efficient, and therefore you could have over approximation of the most precise ones, and that is one source of imprecision. When you do joins, and the joins you do when you have if then else across the two arms of if then else, or when you join while doing clean iteration over loops. Okay, so you will join at the head of the loops, and then when you use widening operator for guaranteed convergence, those are the three sources of imprecision. Okay, one way to improve these imprecision is to use more precise and more complex domains. Okay, and some of these domains I will not in next lecture, because the next two lectures I will be concentrating on introducing predicate abstraction, because that is something that I certainly want to cover. But in one of those lectures, if I finish things, I will introduce you to the different kind of domains that tools use in practice. And you already, I'm assuming that you're using AVA, and you have had a chance to look at some of the domains, abstract domains that it supports, and have some understanding. So I want you to make some progress on having run. By the way, what is the status? I mean, is everyone here? Okay. Yeah, I mean, maybe we can ask that. I want to see if Dhruv, have you made any progress? Have you even run ever, or what is the status? Is Dhruv even here?
Yeah, I can hear you.
Yes.
So I've run AVA, but in terms of the project, the status is not really a lot.
Okay, so I think we only have a few more weeks. Okay, so I think what I'm going to do is, this is just a small digression on the thing. So I mean, the same question to Siddhant and Chandradeep.
Yeah, so we have done everything that, was covered in the tutorials. So everything is set up, basically.
It is set up. Have you run?
Yes.
Run ever to produce, generate some all the inductive invariants?
I haven't
on the emulator.
Yeah, we have run EVA on the emulator.
Okay, so was it successful?
Yes, and we were getting like 200 and something errors.
Okay, that's good. So that is some progress. That's the first thing. Okay, so the first task that you have done. I guess, Dhruv, you guys haven't progressed that much, right?
Yeah, I mean, it's actually what he said, what I did. But I thought that's not a lot of progress.
Okay, so I think, anyway, so I'll communicate to you about the things, because I want to make sure that I want to make sure that you don't fall flat. You kind of delay and then you do. So that is one way to do, is to kind of encourage you, if not force, to submit some interim milestone status kind of a thing, just a small bullet thing, okay, not a big thing. Therefore, that way it will, to be honest. And therefore, let's see. So I want to finish up certain things here, and maybe next, Thursday class, you can use that. Okay? And then if you have any issues, please get back to us. Okay. Yeah. So reducing the other issue with when you use the thing is the issue of false alarms, as you guys already have seen. They produce not all the alarms that they produce after generating the inductive invariance to check some of the design agnostic properties. Standard properties may be actual errors, and therefore you will have to sort them out. Okay. And as this says, the whole idea of this project is to use symbolic execution of the kind that CBMC uses on concrete to generate concrete witnesses for each of those alarms, and see if that can be you can filter out a lot of these things. And that's another kind of thing where tools you can make tools cooperate with each other, and which is what you are looking at. Okay, so that is both things. So the only thing remaining is that I will cover some. I will introduce some about some of the standard domains that are supported by tools. Yeah. Well, these are some of the tools. They are professional tools. Okay, here there is something interprog and academic open source implementation. That's something I totally forgotten about it. Okay, so I don't know. We never looked at it, Diganta. Anyway, we have pharmacy right now. So all these things are production quality tools, and they are not available for free. You have to jump through the loops to do it. Okay, so okay. So any questions so far? Okay. So in that case, then I will at least introduce you to some points. I'll go till 6:15. Okay. So, and then continue the rest. So for this lecture, I'm going to be using a tutorial slides from a tutorial given by Daniel Cronin, who, yes, so this was a tutorial that he gave at the conference. Yeah, so you've already seen one kind of abstraction mechanism, okay, using certain abstract domains that fit certain shapes. Okay. Now, that is one way to do, but there is another way to. All these things. Okay, so there are lots of different kinds of techniques for doing using abstraction things, and this is one way is using abstract domains of that pertain to certain shapes, as we saw, like interval domain and the polyhedral domain and so on. So this is somewhat more general. They're based on predicates. Okay, and this one was quite successfully used. The inventor of this is someone called Hassan Saidi and Graf, Susan Graf. And based on that, this very successful tool was built tool called SLAM, for verifying driver code, hardware driver code at Microsoft, and that is one of the most successful implementations of this kind of abstraction. Okay? So this abstraction in general reduces the size of the model by eliminating irrelevant details, and usually the irrelevant details that you eliminate are done by looking at the kind of properties that you want to prove. In this case, this specific kind of abstraction, as you will see, abstracts a model into a finite model by means of a finite set of predicates, okay, chosen set of predicates, okay, and these, so the idea is to track only predicates on data. In a way, I mean, as I describe this, let me not do the comparison right now. So as I will go through these slides as though this is a new technique, but you will see similarities between this and the Galois connection-based abstraction approach used by static analysis tools. Okay, and we make some points, and then you please make a note of that, and then ask me. Okay, so here is a transition. Here, this predicate abstraction is works not through Galois connection, but it directly abstracts your crypt key model, transition system model that we introduced earlier, and then did all our model checking, fixed point calculations on. Okay, this is technically an infinite transition system whose state components, state variables, range over integers, okay, or natural numbers, let's say. Okay, that's an infinite domain. What I've shown here is only the some part of the the reachable part, and a few other non-reachable states. Okay, because showing the entire thing as graph is not feasible. So this is the initial state, which x is equal to 2 and y is equal to 0, and it increments y, and it stays that in that thing. Okay. Obviously, these other states that I've shown here are not reachable from the initial state. Okay. Now, that is so. Okay, I'll have to. I can't use things on this. So this is what. So now, suppose we are interested in only tracking properties that depend on tracking if x is greater than y or y is equal to 0. Okay, then we could just limit ourselves to maybe tracking these two predicates. Okay, how the valuations of these predicates are on concrete states. Okay, and we can track. Now you see there is already a similarity that you've seen. You saw the and we usually base our abstraction on a finite set of predicates. You already saw something similar to that in the abstract domain, right? For example, your sign domain had only finitely many things. Somewhat, it was tracking whether x was greater than 0, equal to 0, or less than 0. In any case, so the abstraction is defined based on these predicates, and here we have chosen here these two predicates. Okay, now these based on what states that for which what the valuations of the truth values for these predicates are, you can partition the concrete states into classes, partition them into a set of states for which where each state in a partition evaluates those two predicates to the same value. For example, here, these two states are ones in which both P1 and P2 are true, correct? Yes, because X is greater than Y and Y is equal to 0. Here, in this state, X is greater than Y, so P1 is true and not P2, right? Because Y is not equal to 0, and so on. So the abstract states, the abstract transition system, abstract model in our case, the elements of the abstract thing are the different possible valuations for that the predicates can take. So in this case, there are two predicates, and there are only 4 possible values. Okay, so there are only finitely many abstract states, and they are determined by the different possible valuations that these predicates can take. Good. So this one can abstract an infinite domain into a finite domain. As a matter of fact, here, since I have not shown all the concrete values, each of these classes can obviously have all unreachable values. But for example, here, this is something in which this one, it can have other values that other natural numbers for X and Y that can be included. I've just not shown that. Therefore, what I'm saying is that this is an abstraction which abstracts a potentially infinite domain into a finite domain. Okay. Any questions so far? So now, in order to define, so now I've defined how the the elements of the abstract domain is defined. Okay. Now, in order to construct a model, we need to define the transition for this. Okay. How should we define the abstract transitions? That is the transition relation for these things are shown by these edges here. And as you know, that corresponds to, based on these transitions that I've shown, you can define the transition relation as a formula. And now similarly, in order to construct the abstract version of the transition system model, we also need to define two things: abstract transitions and also the initial states, okay, for the abstract transition system. And the way that you do is, and how do you define that? I mean, you'll have to do it in such a way that it has to be an over approximation. Okay, because our idea is to use the abstract model to verify safety properties, invariant properties. And as you know, that in order for that to be done safely, we need to ensure that my abstract model, the traces that it generates, includes all the traces, the corresponding traces of the concrete model, and the reachable states that it generates as such that they all include the corresponding concrete states. Okay, and that's how we'll have to do it. That the traces, the paths, the execution paths are determined by the transition relation, how you define the transition relation, and how you define the initial set of condition. Now, in static analysis, when you use the Galois connection, how did we guarantee that the abstract model that you constructed was an over approximation? Anyone? What did we construct there? Okay, because we defined alpha, define an abstraction function, and I will in a moment I'll define the abstraction function here. Okay, on sets of states there. Okay, similarly we'll have to define it here, but I've just shown it here. They are based on these how evaluations of the predicates. But we defined another thing there. Okay, the abstract transformer. Remember? Okay. And which was actually the abstraction of the post. Okay, the abstract transformer for the post. We did not construct the transition relation explicitly there, but the transition relation is what determines the post. So we did it for the post. So my question is, how did we ensure that the post was defined correctly? Is this the one? Where is it? This is not. Anyone? So while I search for my slide, anyone who can answer that? How did we ensure? Keep forgetting. Yes. Answer. You remember this line? So firstly, we guaranteed that by defining alpha and gamma as a Galois connection, okay? And then we ensured that whatever the abstract version of for f hash, which itself used post and which itself was defined by defining the transition relation in a piecewise fashion, okay, or the post for each of the construct. Remember that? Okay, and that was done such that this was an over approximation, okay, of this thing. So it is through this criteria that we ensured that it was an over approximation. But here we do it a little bit more directly. Okay. So here's how, and what we do is we use the concept of what is called an existential abstraction, existential criteria. It turns out that the kind of abstraction, the criteria that you saw in the other slide that you just now saw is also results in an existential abstraction, but it is stated and formalized in terms of the transition system model, and you will see that the way that it was defined, through Galois connection and the over approximation abstract transformer also satisfies this criteria. So, what is an existential abstraction of a crypt key model? Okay, model. Okay, here is a concrete model M, transition system, set of states, concrete states, initial set of states, and the transition relation. Now we are going to be constructing S hat, S naught hat, and T hat. Okay, we kind of saw how the states of the thing were defined. They were defined in terms of variations for the predicates. Okay, that's how they were organizing things. So, and here we're defining the So don't confuse this alpha here. This alpha here just defines, it is the alpha of that we saw in abstract interpretation was defined on sets of states. So here, so alpha S, what does it correspond to? It is just, it is alpha S gives something which is an evaluation of P1, P2, okay? And so, whatever the value for which S is, that state S is true, okay? For the evaluation for the things P1 and P2. Maybe here, one example here. No. Okay, so yeah, so we define the initial set of states for the abstract model is that if any, so as you know that these are sets of states, okay, each abstract domain element denotes a set of states. If any one of those thing has, so any, if this S, if the abstract state is not, okay, all the states which get mapped, every abstract state which is an abstraction of a concrete state, in the initial state will have to be the initial an initial state here in the abstract model as well. Okay, and that's how it is done. For example, in this and so if there exists any S in S naught such that it's an initial state such that gets mapped to a particular abstract state, then it should be an initial state. Similarly, if there is a transition between two concrete states, then there must be a transition between the corresponding abstract states that the concrete state gets maps to. So if S maps to S hat and S prime maps to S prime hat as per the mapping here, okay, based on the predicate evaluations, then you will have to do. Okay, so that's what. So you will have to note that don't confuse this alpha with the previous alpha. This alpha is mapping individual concrete state to an abstract state by actually evaluating the predicates on the concrete states, as we did to group the concrete states here in this picture. Okay, of course you could, this alpha on individual concrete states automatically induces an alpha on sets of concrete states as well, and as we will see, and that was what was being used to define Galois connection in the abstract. So this one says when there must be a transition edge in the abstract model. Okay. Now it doesn't constrain. You could add more transitions, just like in the while constructing the abstract transformers. You could construct it in the most precise fashion, or you could even further over approximate it. Here also you could throw in more states as you wish into the initial set of states at the abstract level, or you can add more transitions than required as well. Okay, but if you do only the minimal number of transitions that are required, and you include only exactly those things that definitely need to be required as per this criteria, existential abstraction, then what you get is the minimal among those abstractions. Okay, So let me, quickly move to the example. Okay. So this was the thing. So so the abstract, the initial, what should be this set of initial states? Okay, in this case, there's only one concrete state that is initial. And since this abstract state here shown in blue contains a concrete state that is, that is an initial, in this case, the only initial state in the concrete model, this, this whole thing has to be, and I mean, so this state, P1, P2 will be an initial state, since the concretization of this P1, P2, so the elements, the set of all elements that get mapped into P1, P2 includes an initial state. Therefore, this whole thing is an initial state. Okay, and that is the only initial state. Now, for example, if one of these states were an initial state in which P1 and P2 are false, then you would have had to make this also as an this abstract state where P1 and P2 is 0, 0, also as an initial state. Okay, in this case, this is the only thing. Of course, you could make more things as initial if you want. That will create even more abstraction. Okay, so how is the transition relation defined? Okay, then the transition relation, if there exists a transition between any two concrete states, then the abstract state to which these two states get mapped to, the predecessor and the successor of each transition, there must be a transition between those states. Okay, so you will have to have a transition between P1, P2 to P1 not P2, because you want to ensure that every transition that you can make in the concrete is also simulated by in the abstract model. So there must be one here. Okay? And the only other transition in the concrete state is a self-loop from this state to itself. That is mapped to, that is the only state that gets, that is reachable here. In this case, P1, not P2, and therefore there must be a transition between that. Yeah. Before I get to that, okay. So there is a transition between, the concrete state x is equal to 1, y is equal to 0, and here, and therefore there must be a transition between P1, P2 states and not P1, not P2 state. Okay. And finally, there must be a transition in the abstract model to itself, into the state, because there is a concrete state in which there is a self. Okay, so that's how you construct the abstract model. Any questions on how you construct?
There should be a self loop in the bottom too as well, right?
Here, in the not self loop in not P1 to not P2?
Yes.
Let's see. So,
Since there is a concrete state that goes to another concrete state in the same.
Correct. Yes. That's a good observation. Yes. There exists a state. Yes, there must be one, because there is a transition. Right. Yeah. Okay. There must be one to itself. Yes. Good point. Okay. So there is one thing. I forgot. Okay. Yes, you're right. Yeah. Okay. And that is so that is a transition. You're right. Okay. So I had missed the. Now the idea is once you get it, so this kind of using existential thing will ensure that if we have a path, if there is if there is a path in the concrete state, I mean the concrete model, for every path in the concrete model, there is an abstract version of that path in the abstract model. Why? Because you can actually prove this by because we have ensured that whenever there is a transition between S0 and S1, the concrete state S0 and S1, if there is a transition, then there exists a transition between the abstract states that S0 and S1 get mapped to, and therefore there must be a path from alpha S0 to alpha S1 as well. Okay, and that induction, if you use induction, that will be true for every pair, every successive pair of nodes here that are connected here. Okay, and that's why this is an over approximation. Okay, so because if there is there can be, of course, the abstract model can have more paths that are not there in the concrete model. Okay, like and therefore, since every path in the concrete model has a corresponding version in the abstract model. Okay, so there's a question. Okay, so in that case, let me, I've gone beyond 650. So I think I should stop here. Okay, so so this ensures that this is an over approximation. So let's, so this over approximation is a requirement to ensure that safety properties and invariant properties are preserved, okay, in the thing. Okay, so I'll stop there and I'll continue tomorrow at 2 o'clock. Thank you for your patience.
Thank you.